In this video, I want to cover random variable algebra and why it's important. I really also want to build an intuition for you using sampling and an applied example, and I want to show you the various ways that it can go wrong, one way you can use to help yourself find sort of the right path, and compare this to the way, let's say the gold standard way, which is math. Now, math is the best way to go because it's always exact and it's well proven and well defined. But random variable math in particular can be very hard to understand. It's a little bit of a niche topic. It's not necessarily covered even in high schools all the time. And if you go to the Wikipedia article here, you see all these symbols that may not necessarily make sense. Even the Wikipedia article itself acknowledges this. I mean, this article has been flagged for over a decade now to be challenging with citations and confusing to readers who are unfamiliar with statistics. The challenge, though, is these concepts are relevant in many situations, and they're particularly relevant to every data person. But I think because they're sometimes hard to understand either why it's important or how to use them, they just get ignored entirely. So again, we're going to build an intuition using an example and simulation to clear things up. Now I want to say this is not a shortcut to avoid the math entirely. I'm just not going to cover the math here because other people have done a fantastic job covering it, let's say the traditional way in textbooks and whatnot, but also in videos. So I've left 2 links here if you want to take the math approach. Actually, when you want to go look at the math approach and understand the fundamentals of what we are doing here. Oops. So let's start with our applied example. We want to determine what amount of vaccine we need to vaccinate 1 million people. If you're watching this video anytime in the vicinity of 2021, I'm sure 2022, you recognize this is relevant to the COVID-19 challenge that we're facing right now. Well, we're just going to take a little bit of liberty and assume a couple things. We just need 1 dose of vaccine for each person, and we'll ignore this sort of vial constraint or anything like that. We'll just assume we need to know what amount of vaccine we need to have in a big vat to vaccinate enough folks. Now we can see the methodology here that even Pfizer has put in their manual. A doctor is supposed to take a syringe here, and they're supposed to pull out 0.3 milliliters exactly to give to somebody. Now with those 2 numbers, we can sort of figure out what we need, right? Each dose is 0.3 milliliters. We need to vaccinate 1 million people. So we're going to need 300 milliliters of vaccine. Well, 1 dose is 0.3. We have 1 million people. We multiply the 2 together, and we get 300,000. It shouldn't be too surprising for anyone that's made it past even an elementary school education. The cool part is we can use Python to do the same thing. We define our variables here, 0.3 and 1 million. We multiply the 2 together, and we get our number again, 300,000. Easy peasy, right? Things are simple. The problem is everything in life is random. If you've got these medical professionals and these doctors, they're trying to vaccinate 1 million people as quickly as they can. They're pulling out 0.3 milliliters, which isn't that much of volume. They're going to make a little bit of a mistake, right? They're not going to get exactly 0.3 every time. But we need to still figure out what the amount we need is for 1 million doses. And the way we're going to do that is we're going to have to define this imperfectness, also known as random outcomes, if we want to do the math correctly. Now, similar to the previous example where everything was deterministic, which was 0.3 each time, we need to make a definition of what we're working with. And this is what a random variable is. A random variable defines the idea of these random outcomes that produce samples. So we'll see an example here in a second. But what we're gonna assume is that our random variable is a Gaussian distributed random variable. And down here in the middle of the slide, we can see the math that you may see in textbooks, the n and the mu, which signifies the mean, and the sigma, which signifies the standard deviation and how much things vary. And we can also take that same idea and we can encode it in Python. We take our random variable called dosrv and we define it with stats.norm with a mu, which is the mean, and a standard deviation. And we can even, because it's in Python, pull a random sample out and see what we get. In this case, one random sample is 0.27. Now, the important thing about random variables is random doesn't mean truly random, like we have no idea what's going to go on. A lot of random variables can be defined in certain ways. So we had picked a Gaussian distribution to define this particular random variable, and we can plot that down here. And what this tells us is the probability, the relative occurrence that we expect different sort of vaccine doses to happen. So we expect 0.3 to happen most of the time, right? That's exactly what the health professionals are shooting for. We expect 0.1 to happen much less frequently, maybe not, very little or not at all. Same thing over here, maybe at 0.5, but maybe 0.25, 0.35. These dose amounts may occur because, again, as these medical professionals are pulling vaccine doses, they're going to err a little bit here, they're going to err a little bit there, and we believe we'll end up with this sort of distribution of random outcomes from this particular process. Now, a great thing about computation and computational statistics is we can use the computer to help us learn things. So in this case, if we just had our random variable and we didn't know what the mean or we didn't know what the standard deviation was, let's say somebody just handed you 10,000 recordings of vaccine dosages, we can figure out what the mean and the standard deviation are. We take our random samples, we take the mean, we take the standard deviation using mathematical formulas that are not shown here, or in our case, using a computer which has encoded these mathematical formulas, and we get the mean out, which is 0.3, and we get the standard deviation out, which is 0.05. So simulation can help us learn things about our random variables and sort of abstract the math away from us, which is very, very handy. But we're not so concerned with the distribution of a single vaccine dose. What we need to figure out is how much vaccine do we need for 1 million people, right? And this is where the algebra comes in, just like before. Before we use multiplication to take our deterministic 0.3 and come up with 300,000. We need to do the same now with a random variable which is a normal distribution describing our vaccine dose. So this should be easy. Like I said, we just multiply our random variable, right? Well, it gets a little tricky. The first wrong way that I've seen be done is you just take the parameters, the mean and the standard deviation, and you multiply them both by 1 million. This, really feels intuitive. It feels like it makes sense. We've been so used to multiplying numbers for so long, I feel like we can just do the same thing here, but it's definitely wrong. In this case, it happens to be right just for the mean, but it's very wrong for the standard deviation. The next way we could do it is multiply a single sample by 1 million. So I've seen folks use their computer to take a single random sample, and then they multiply it by 1 million and say, okay, we're going to need 260,000 milliliters of vaccine because I did simulate this. Well, what you're really doing here is you're simulating one random outcome, and then you're just deterministically assuming that every random outcome, the next 299 million X, are going to be exactly the same. And that's not what's going to happen in reality, right? In reality, every single of these million doses of vaccine are going to be subtly different, and we're not accounting for that here. The third wrong way is you do take 1 million random samples. So say we take our dose random variable, and we do take a million random independent samples like we have here, and we just add them together. Well, this only tells us what would happen in one sequence of 1 million doses, but it doesn't tell us what could happen in another sequence or any one of the infinite sequences that could occur. So this is a great single trial, let's say, of what could happen, but it doesn't tell us everything that could possibly happen. Even mathematically, with a single number, sure, we can get one outcome, but how do we calculate the standard deviation from here? Where do we go? So if we were to simulate this random variable algebra, the way we would do it is we would take 10,000 simulations of 1,000,000 vaccine doses. It's a lot of numbers. It's a good thing computers are fast these days. So you see that here in the loop. We declare a number of trials on the outside, and we say for every trial, we're going to take 1,000,000 hypothetical vaccine doses from our random variable, the simulation, and then we're going to record that, and then we're going to do that another 9,999 times. And through that simulation, we can then back out what the mean is going to be. So it's going to be close to 300,000, just like we expected. But we also get what our standard deviation is. In this case, it's 49.8, which is really close to 50. I'll note that some people might comment this loop is not vectorized in NumPy. If you're one of those people thinking that, this is just for clarity's sake. But we'll just take it as it is and we'll move on. So the simulation was fantastic. It gave us a number. And in this case, it actually happens to give us a number that's very close to the analytical answer. So if you could read the random variable algebra in mathematical form as we've shown here below, with the var z and the var x plus y and the two covariants x, y, you could just apply the formula directly just as we've shown here. You take the standard deviation, you convert it into a variance, you add it 1,000,000 times because multiplication is just addition that's been replicated, and then you take the square root and you get the same answer. But again, we're in this video. If this doesn't make sense, don't worry. We're in this video because it's not necessarily the most intuitive thing. But we do and we can use the simulations to help us understand the math and pair the simulation with the math to understand what could be going on. So simulation isn't perfect, unfortunately. Simulation is not guaranteed to be exact. It's not even guaranteed to be close. You have to take many samples with simulation to come up with potentially even the right answer. And how much is enough is not even an exact science. The good thing with modern computers is you can put very large numbers in and get an answer really quick. So if you do things correctly, it's not too hard. But just know it's not guaranteed. With simulation, you also don't get a fundamental understanding of what's going on. The great part about math is once you unlock your understanding bit by bit, you gain these building blocks to build more and more complex intuitions up in a sort of cohesive and consistent framework. Simulation doesn't give you that cohesive and consistent framework, which is why the math is still very important, and the math is still the fundamental thing to try and get at. And the last one is it is really easy to just make a subtle typo and get an answer and believe you're close. So if you're going to do simulation, you should just triple check, quadruple check your code to make sure it really is simulating what you think it is. Just like in these previous examples where there were 3 wrong ways in one sort of correct way. So in practice, if you were, say, a working professional, I would check if you need random variables, see if the thing that you're measuring has a lot of variation, has a lot of inconsistency, and if it doesn't, if it's very sort of consistent, then just avoid random variables and do the deterministic math like we learned in elementary school. But it's always worth the double check. Don't just take the mean in your Excel sheet or in a SQL and assume that there's no variation. In some situations, it really matters, as we've seen here. And if you're learning, my advice is learn the math as much as you can. Again, it's a really good idea to learn the fundamentals and learn really what's going on from the core definition. But the good news is in the modern world like we have, you can use your computer to simulate and help that aid and build your understanding. If you happen to be in industry as well and you don't have enough time to learn, you can use simulations to get where you need to go. But I would still advise you to come back and try and learn the math. Well, I hope this helps. I hope this adds a little bit more clarity and another angle that you can use to understand this very important and very applicable portion of statistics. I personally think statistics is awesome. It's described so many things that I've worked on, from rockets to salads to oil tools to just everyday life, like this COVID situation, for example. If you like this content, find me on GitHub or Twitter. I'll continue writing about this, or you can find my blog right here. Thanks.